Hello, in this video we're going to continue on with our introduction to hypothesis testing, but the objective now is our student-led example. So if you haven't already, hopefully you've already downloaded and printed out the teacher-led and student-led example and followed along with the teacher-led example in the previous videos. So our objectives are still the same: to understand the logic of hypothesis testing, to state a hypothesis and locate the critical region, and to conduct a two-tailed z-test and make a decision. But now you guys are going to take the lead. So please pause the video and work through the problem yourself before watching me work through it. So again, go ahead and pause the video, work through it, and then watch my solution. So here's the example that you just completed. Researchers are interested in the effects of instructions on timed school achievement tests. The researchers give the test to 64 randomly selected high school juniors. They give the test in the usual way, except they add to the instructions a statement that the students are to answer each question with the first response that comes to mind. When given in the usual way, in other words, without the added instructions, the test is known to have a population mean of 200, so the normal population mean is 200, and a standard deviation is 48. The researchers find that students who are given the special instructions have a mean of 220. So we want to calculate the significance for a two-tailed hypothesis test, and we'll make sure to include the hypothesis and the correct way to report that in the literature as well. So let's highlight the important information. So we have the important information that we have highlighted. So we have an N of 64. We have a population mean of 200. We have a standard deviation of 48. That's here. And we have a sample mean of 200. So now we're going to go through those same steps that we went through in the previous video. The first step is to state the hypothesis. So the first thing we're going to do is state the hypothesis. And remember, we said that the mean was 200. So that means that our null hypothesis is going to be that the mean of the treatment is going to equal the mean of the population, or that the mean of the treatment group equals 200. So that's our null hypothesis. Our alternative hypothesis is that the mean of the treatment group does not equal the mean of the population. In other words, the mean of the treatment group does not equal 200. Next, we need to set the criteria for our decision. And just to be consistent with what we've done in the past, we're going to go with a p-value of 0.005. So let's look at our unit normal table and see if we can find that 0.005. So here we have 0.05, proportion of the tail. Now, is that the right value? 1.64? Remember, we're doing a two-tailed test where we have one boundary here, and we have two critical regions. So we need to take that 0.05 and break it into two. So we need the table that looks like this, where we have 0.025 giving us a critical Z of 1.96. All right, so now we need to collect the data and compute the sample statistics. Here again, we've highlighted the important information that we've needed. We wrote down already what that important information was on a previous slide. So we're going to jump ahead here, and I have it all written out here nice and neatly. This is our N, our population mean, our standard deviation, and our sample mean. So what we need to do first is calculate the standard error. So here, the standard error equals 48 over the square root of 64. So that's going to end up equaling 48 over 8, which equals 6. Then we need to calculate our z-score. So here we're going to put in our sample mean, which is 220, minus our population mean, which is 200, over our standard error of the mean, which is 6. That's going to give us a calculated z-score here. So if I do all those calculations, of 3.33. So now let's remind ourselves what these numbers are. We have a critical z and we have a calculated z. The calculated z from the previous slide was 3.33. Now a critical z, that was those boundaries that we had here, right? So these boundaries are demarked by the critical z, and here we have two critical z's because we have a two-tailed test, and then these are the critical regions out here. So that critical z for an alpha of 0.05 is 1.96. Plus or minus, better, 1.96. So 3.33 is greater than 1.96, telling us that it's out here, right? It's really far out there, which means that we need to make our decision now. So among high school juniors, because that was our population, special instructions for the student achievement test significantly increases test scores. And then we would write our z equals our calculated z-score at a p less than 0.05. So this is how you would report it in the literature. So we reject the null hypothesis. So that's the other important thing here to note, is that we are going to reject the null because our calculated z is bigger than our critical z, meaning that it's out here in that critical region. So now that you've been successful on doing the teacher-led example, the student-led example, go ahead and try practice problems 1 through 6, and we'll go over them in the next Zoom session.